So let's talk about reaction mechanism for just a few minutes. This will be your introduction to reaction mechanisms. And so what the reaction mechanism is a series of elementary steps by which a chemical reaction occurs. Now, normally when you're given a chemical reaction, you will see the overall net chemical reaction. You will not see the mechanism. Now, for this unit in kinetics, we want to think about what steps are necessary in order for a reaction to take place. And so when you're looking at a mechanism, the mechanism must satisfy two requirements. The first requirement is that the sum of your elementary steps, when you add the elementary steps together, they must give you the overall balanced equation for the reaction. The second criteria that must be satisfied for a mechanism to be what we would call probable or valid is the mechanism must agree with the experimentally determined rate law or the observed rate law. So that rate law would have been determined using one of the strategies like method of initial rates, or maybe even looking at some concentration and time data. But the mechanism, for it to be probable or valid, it must satisfy both of these requirements, not just one, but both. So the sum of the elementary steps must add together to give you the overall balanced equation, and the mechanism must agree with the experimentally determined rate law. Now, one thing we also want to look at and understand is what is meant by the rate determining step, and that will be abbreviated RDS, the rate determining step. The definition of the rate determining step in a multi-step reaction is that it is the slowest step in the mechanism. So if you're given 2 or 3 or 4, even 4 elementary steps, the slowest step in the mechanism is considered the rate determining step. It therefore determines the overall rate of the reaction, because the overall reaction cannot be faster than the slowest step in the sequence. Sort of like if you're running relay, thinking in terms of track. You're on a relay team. If you have your relay team is running around the track, your overall time can't be any faster than your slowest person. That's the one that's going to hold you back. So the rate determining step is always the slowest step in the mechanism. The experimental rate law must agree with the rate determining step. The rate law of an elementary step can actually be written from what's called its molecularity. Let me repeat that. The rate law for an elementary step, now not an overall reaction, but if you're given a mechanism with elementary steps, you can actually write the rate law directly from its molecularity. So we need to clarify, or I need to clarify for you exactly what is meant by molecularity. Molecularity is referring to the number of species, the number of particles, the number of reactants, if you will, that must collide in order to produce the reaction indicated. Again, the molecularity is the number of species that must collide in order to produce the reaction indicated. So we're going to take a look at some elementary steps. We're going to take a look at how we would describe their molecularity and how you could write the rate law from the molecularity of the elementary steps. Now keep in mind, the only types of reactions you can write a rate law directly from without using experimental data is if you are told that it is an elementary step in a mechanism. So if you're given, I'll number these elementary step 1, 2, 3, 4, and 5. Okay? So for elementary step 1, if you're given one reactant yielding products, and keep in mind when we're thinking in terms of your rate laws, we're considering a time where the reactants are the only concentrations to be considered. So if A is yielding products, If this is your only reactant, there's one reactant, we call that a unimolecular step, meaning one molecule is involved. So since it's unimolecular, we would write the rate law of that as rate equals K times A to the first power. First order, because it's unimolecular, so the order is 1. Now again, you can only write a rate law from a elementary steps molecularity. You would have to be told it was an elementary step and it was a mechanism given. Another option is with an elementary step is if you have two reactants colliding. If they're two identical reactants, you could abbreviate that as 2A, your coefficient 2A. But nonetheless, if you break it apart, it's two of the same type of reactant colliding. This is considered a bimolecular reaction. And so you would write the rate law straight from its molecularity. Since it's bimolecular, it would have an order of 2. So rate is equal to K times concentration of A squared. So bimolecular elementary steps have an overall order of 2. Now another option of a bimolecular is if you had two different reactants colliding, one particle of each. So one particle of A colliding with one particle of B. Two total particles makes it bimolecular. So you would write the rate law, rate is equal to K times concentration of reactant A to the first power, because there's only one A, and times concentration of reactant B to the first power, because there's only one B. Now, if you add the overall order together, 1 plus 1 gives you 2. So you still get bimolecular has an order of 2. These are the most common, first order and second order, and even we've talked about zero order, which we're not representing here. But you could have a fourth and fifth option here, where you have what we call a termolecular. So one example would be if you have reactant A, and reactant B. So two of the same reactant and one of a different, or another termolecular is reactant A, reactant B, and reactant C. That would be another termolecular. Notice there's 3 different reactants there, or 3 reactant particles colliding in this elementary step. So you could write the rate law as rate is equal to K times A squared, since there were 2 of A, times concentration of B to the first. If you add these orders together, 2 plus 1 is 3, you get third order overall. And then finally, if you were to have A plus B plus C, 3 different particles colliding, forming your products, that's still termolecular, and you would write the rate law for this elementary step is rate is equal to K times concentration of A to the first times concentration of B to the first times concentration of C to the first. Notice the overall order is 3 because 1 plus 1 plus 1 gives you 3. Now in the next video, we're going to pick up with how you can identify your rate determining step from a given set of data.